I wanted to backtrack just a little bit and say one more thing about carbonyl chemistry. The one thing we didn't really get to was 1,4 addition. And this is where you have a nucleophile attack the beta carbon of an alpha beta unsaturated carbonyl compound. And of course, if you remember from our first exam where you drew the molecular orbitals of acrolein, you know that that there's a substantial amount of LUMO on the beta carbon. We'll talk in just a minute about which nucleophiles prefer to attack where. And this nucleophilic attack is the slow step, and it's reversible. And then it turns out, this is kind of interesting, I didn't actually know this, it's faster to protonate on heteroatoms than it is to protonate on carbon. I didn't know that. So what likely happens here is that first you protonate the oxygen in your enolate, and then in a second step you tautomerize to the more stable ketone. And I won't show you how to push arrows. I think you already know how to do that. I just didn't know that it was faster to protonate on oxygen. So if you've ever seen, if you've ever seen in your undergrad organic chemistry textbook them show you, oh, it goes to the enol first and then tautomerizes to the more stable keto form. And if you've asked, well, what's the whole point of doing that? Couldn't I just protonate directly on the alpha carbon? And the answer is sure you could, but what actually happens is probably you you protonate the oxygen first, you get the enol, and then you tautomerize to the keto form. Incidentally, looking at this enol is the one way you can understand why on earth this is called a 1,4 addition. Start with 1 on the oxygen, 1, 2, 3, 4, and the things you add, proton and nucleophile, are on atoms 1 and 4. And this can be contrasted with conventional carbonyl chemistry, wherein a nucleophile adds to the carbonyl carbon, and then you get an alcohol as your product. And again, we are going to call that 1,2 addition because the stuff that we've added across that carbon-oxygen pi bond are on atoms 1 and 2, respectively. Questions about that? Anything look unfamiliar? This is often called conjugate addition or 1,4 addition. It is also, in the case of using a carbanion or an enolate, called Michael addition. In practice, most chemists will use the term Michael addition for any conjugate addition, so there isn't as much of a distinction about that. In terms of whether a nucleophile will add, given a carbonyl compound, whether a nucleophile will add to the beta carbon or the carbonyl carbon, it can depend on sterics and the presence of nearby electron withdrawing groups. So to some extent, this needs to be evaluated in a case-by-case basis. However, the major factor is the identity of the nucleophile. And again, this is something I didn't really know. And to distinguish which nucleophiles will add where, we're going to go to hard and soft acid base theory. Soft nucleophiles, remember these are nucleophiles that are not highly basic. They are generally large and polarizable. These include thiolates, that is negatively charged sulfurs. These include amines, enolates as well. And these will prefer 1,4 addition simply because most of the LUMO is on the beta carbon. Hard nucleophiles are those that are small, not particularly polarizable, very basic. These would include organolithium reagents, Grignard reagents, alkoxides probably. These prefer 1,2 addition, and in many cases it is because the counter ion, like lithium or magnesium bromide, is coordinated to the carbonyl oxygen, which tends to keep the anion close to the carbonyl carbon. So that's an interesting rule of thumb. I suppose we should include in soft nucleophiles the cuprates, because when sophomore organic, I remember teaching that, okay, Grignards and organolithiums attack the carbonyl carbon, whereas cuprates attack the beta carbon, and then we later learned that enolates attack the beta carbon. Why is that? I didn't know. It was something you had to memorize. In this case, it has to do with either the counter ion coordinating the oxygen, which promotes 1,2 addition, or for softer nucleophiles attacking the beta carbon. So that's something that I learned and thought would be useful to share. Anything you want to ask about that? No? Okay. So if you remember last time, we talked about, we spent a huge amount of time, unfortunately, on the Berge, oops, I didn't want to cut that. I wanted to copy it. The Berge-Dunitz angle, and so I'm going to copy over a page just so that we have it and can talk about it. Recall that the Berge-Dunitz angle describes the approach of nucleophiles to carbonyls, and that preferred trajectory is about 105 degrees if you're attacking a carbon-oxygen pi bond. Turns out that angle is also preferred for 1,4 additions if you're attacking an olefin. And the reason for all of this is that that's where the pi star is. So I think these are images I didn't show you last time, but here is the sigma out orbital on a nitrogen in methadone. Here is the carbon-oxygen pi star. And you can see that the pi star is angled back and away from the carbonyl carbon, and that as the nucleophile approaches along that Berge-Dunitz angle, you've got substantial orbital overlap between the lone pairs on the nitrogen and the pi star. So the Berge-Dunitz angle is all about, you got to attack that from that direction because that's where the pi star is. And this actually influences the efficiency of various cyclization reactions. Because in order for a cyclization reaction to occur, you have to have a nucleophile attack an electrophile, and it needs to be able, the filled orbital needs to be able to reach sorry, like a broken record, the empty orbital. And not only reach it, but reach it with the right geometry and orientation. So this is the reason behind a set of empirical rules of thumb that are called Baldwin's rules. And Baldwin's rules define different types of cyclizations, categorize them by ring size, by hybridization of the atom under attack, and by whether how to explain it? Maybe it's best to explain it with some examples. So suppose you have an enolate and you want to do an intramolecular aldol reaction. Okay, the ring size here is 1, 2, 3, 4, 5. The hybridization of the carbon that's being attacked is sp2. And then it turns out that, of course, the carbon that we're attacking ends up being part of the ring. There's really no other way to do that. However, the other carbon in the bond that was attacked, the other atom in the bond that was attacked ends up outside of the ring. Okay, so actually let me just highlight that atom in, say, orange. Okay. So here's the atom that was attacked. It was sp2 hybridized. And then the other atom in the bond that was attacked is now outside the ring. So we're going to call this an exo ring closure because the other atom of the bond that was attacked is now exocyclic. Okay? And to make things more confusing, if the atom that was attacked is sp2, we're going to use the phrase, the word trig. And so we're going to call this a 5-exo-trig cyclization. I think I pretty well murdered that. So what questions do you want to ask? That's right. That's right. So exo refers to the fact that the oxygen's outside of the ring. Trig refers to the fact that the carbon we attacked was sp2 hybridized. Okay, what else? Right, so if it's sp3 hybridized, we call it tet. If it's sp2, we call it trig. And if it's sp, we call it dig. I didn't make them up, I'm sorry, but those are sort of the rules. Another example of a cyclization might be, we could take this same example and keep it almost the same, only let's, instead of having us attack a carbonyl carbon, let's have us attack an sp3 hybridized carbon that has a leaving group on it. Okay, so again, we can define the cyclization by how many atoms are in the ring, and that we form 1, 2, 3, 4, 5. All right, so we'll draw a pentagon, and here is the atom that was attacked. The atom on the other side of that bond is now way outside, permanently disconnected from the ring. So 5 atoms, this is a 5. Should it be endo or exo? Exo. And how'd you know it was exo? Yeah, because the other atom in the bond that was attacked is outside the ring. And then what designation should I give it over here for the hybridization of the atom that was attacked? Tet. Good. So that is a 5-exo tet cyclization. Now, who cares, right? Who cares about having these designations for describing rings? It seems like a lot of trouble. Couldn't you just say, well, I'm making a 5-membered ring? Yes, but it turns out there are trends based on ring size, based on atom that's attacked, and based on whether it's exo versus endo that describe whether a cyclization is favorable in the first place. So we're going to write out a little table here. On the left, we're going to put ring size. And we'll start with the smallest ring possible, 3, 4, 5, 6, 7. And we won't really go more than 7. And we're going to, over here, write our 2 possibilities for whether the other atom in the bond that is attacked ends up inside the ring or outside the ring. And then here we're going to put the various hybridizations of the atom in the ring, whether it's sp hybridized, sp2 hybridized, or sp3 hybridized. And we'll do the same over here, although we can't use tet over here for endo. Why not? Does anybody see a reason why you couldn't actually ever have an endo cyclization with a tet or sp3 hybridized carbon? Yeah, that's exactly right. So in order for this to happen, I would somehow have to attack bromine. And if I made a ring there, then there would be too many bonds to bromine or too many bonds to carbon. Yeah, it just doesn't work. So that's why we're omitting that. That's right. With an endocyclization, well, nothing gets kicked off, I think is a good way to think of it. Maybe I should actually give you an example of an endocyclization. That's right. And the designation endo versus exo has to do with, does the other atom in the bond that was attacked stay inside the ring. So I'm going to give you an example of an endocyclization because I think it's hard to think about conceptually unless you have an example. So this is an alpha-beta unsaturated carbonyl compound. And if we use a base, it turns out you can do the intramolecular Michael reaction where the carbonyl oxygen attacks the LUMO of the carbonyl compound at the beta carbon. And then we'll just speed up and say we protonate on the alpha carbon through an enolate intermediate. Your product would be a 5-membered ring containing an oxygen, an ether, and it would look like that. Notice that the atom that gets attacked is the beta carbon. The other atom in that bond is the alpha carbon, and both beta and alpha carbons are part of the ring. So this has to be an endocyclization. It's 5-endo, and we'd actually call it DIG because the atom that was attacked is sp2 hybridized. So that's an example of a endocyclization where there isn't a leaving group because it's an addition reaction. It's sort of hard to figure out how you could do an endo type of cyclization for a reaction that was just merely substitution. I can't think of an example. That doesn't mean there aren't any. It just means I don't know. All right. So now we're going to use a check mark to describe a cyclization that is favorable. By favorable, we mean has decent kinetics. You can observe it in sort of real time. Unfavorable will be reactions with, we'll use the X, and that'll be for reactions that don't work particularly well. So we'll start with exo-tet cyclizations. These are sort of SN2 type reactions, and interestingly, all of those work. And this is maybe something that you've already thought about, or at least already noticed, because back in 351 and 352, we used to make rings all the time, sometimes with substitution reactions, and we never worried about whether or not the ring would work. And that is because if you're, we'll go back to an example of a tet cyclization. If the atom that's being attacked is sp3, and the atoms in between, atoms 1 and 5, are all single bonds, this is flexible enough that you can get the carbon-bromine sigma star in the appropriate location to be attacked by the nucleophile, right? So there aren't really that many geometric constraints for substitution reactions as long as your ring size is going to be 3 or bigger, and that's convenient because 3 is the smallest ring you can make. Yes? So there isn't any such designation for the Baldwin's rules. A counterexample is this one, where 2 of the atoms in the ring are not single bonds. So I guess it's a little bit of, you have to use a little bit of common sense. If there were double bonds in here such that the geometry would prevent a cycle from happening, say as a trans double bond, there's no asterisk on the Baldwin's rules to account for that, but you just use your common sense to say that the geometry wouldn't work. Yeah. Okay. And it turns out that all of the exotrig cyclizations are good as well. And you can think of these as mostly being 1,2 additions to carbonyls. And the reason that works is, if you look at it, is that even at very small ring sizes, even if the ring size were only 3, your nucleophile could be sort of in the right space to approach that pi bond from the Bürgi-Dunitz angle. Okay. In contrast, ring size matters for the exo-dig cyclizations. And the reasons 3 and 4 don't work is that if you look at an alkyne, 1, 2, 3, 4, 5, it would be pretty hard by atom 3. There would be no way actually for atom 3 to attack atom 1 in a way that would put atom 2 outside the ring. It just by definition can't happen. And even then, at a size of 4, it's difficult to do. All right. Though at other ring sizes, surprisingly, it's fine. The other place where there's a little bit of trouble is in the endocyclizations. So it turns out they're all okay for sp2 hybridized systems. But again, if you use an alkyne, they are only favorable for the larger rings. You can think of these as being 1,4 additions. So this is not anything to memorize. However, you will often hear people talk about cyclizations and say, okay, this is a 5 endo-trig cyclization. In fact, anybody, yeah, go ahead, Kim. That's right. Oh, did I screw that up? Yep, I did. Did I get my... I was wrong here. I'm sorry. So I'm going to just back up. And I'm going to say, surprisingly to me, I actually don't understand this. It says, the table says that the dig cyclizations, that is where you're attacking an alkyne, are always favorable. And if you look at a table, it suggests that somehow a situation like this ought to be able to work, where this leans over here and attacks that to make a 3-membered ring. I don't have any good examples of that. It seems like it shouldn't work. Likely it requires high enough temperatures that this thing is really flopping around and no longer linear, but I don't understand that one. More relevant, I guess, is that the trig cyclizations, the endo-trig cyclizations, don't work except for 6 or 7-membered rings. That is, if you compare the situation we have here, the 5-endo dig cyclization that I showed you, and then you say, well, okay, what if we had a double bond there instead of a single bond? And 1, 2, 3, 4, 5, it turns out this reaction doesn't happen, which kind of seems weird to me, again, because it seems like the molecule with the alkyne shouldn't be more flexible, but it has to do more with where the orbitals are. If you think about the alkyne, you have 2 sets of pi orbitals that can be attacked, some of which are conjugated with the carbonyl oxygen, and the others which are actually pointing toward this oxygen. So I think that's how this cyclization is able to occur. In contrast, if we're to draw sort of the pi system on the carbonyl, and we'll try to draw the LUMO of that, I forget, something like this. The oxygen can't really reach around and get above that pi bond at the Berge-Dunitz angle. It doesn't work particularly well. Okay. So these are, the text points out that these are rules of thumb. They're based on empirical observations. There are plenty of exceptions. There's nothing really theoretical that says that this has to be the way it is. But you will still hear scientists, synthetic organic chemists, talk about cyclization reactions, and they'll use this nomenclature, and so it's useful for you to know what they're talking about. For example, the radical, let's see, the immunyl radical project in the Castle lab, I believe involves a 5-exo trig cyclization, and they'll talk about it in that way. Oh, are you on that? Okay, yeah. Dakota works on that. Did I get that right? It's something like you have some kind of 1, 2, 3, 4, 5, something like this, right? Yeah. Yep. So and they call that, again, 5. It's a radical 5-exo because the other bond ends up outside the ring, and trig because it's an sp2 hybridized carbon. And I honestly don't have Baldwin's rules memorized, but people that care about cyclizations probably do, or they have a sense for what's favorable and what's not, so that if you say, yeah, this is a 5-exo trig cyclization, they'll go, oh, okay, all right, I know. So it's just part of the lingo. All right, let's be done with that. There's some stuff about carbenes that I think is interesting, but I'm going to skip over. So I apologize if you're really interested in carbenes. They can do cyclopropanation reactions, so if you want to know more about that, go ahead and look at them. I did want to spend some time talking about elimination reactions now. We've done addition reactions. Now let's do elimination reactions. And every time I hear the word elimination, I think of the minions at the beginning of the Despicable Me movies with their Illumination stuff. Anyway, sorry. A good example of eliminations reactions involves making carbonyl or carbonyl-like intermediates. Now, this probably isn't the first kind of elimination reaction you've thought about. You might have been thinking about E2. But if we work our way through acetal hydrolysis, we rapidly find some elimination steps. So we're not going to draw the whole mechanism for acetal hydrolysis because you've done that before and you should be really good at it. So here's a situation where you have in green a leaving group attached to a carbon, and we'll call this the carbon that is alpha to the leaving group. And then here is the beta atom that is beta to the leaving group. And when there are lone pairs or extra electron density on the beta atom, those lone pairs can dump themselves. Why can't I move that beta? I don't care. They can dump themselves into the antibonding orbital between the leaving group and the alpha carbon to create a new pi bond, and the leaving group leaves. You may not have thought about this kind of chemistry step as an elimination reaction, but it is, and we could call it a beta elimination. And the product of that is a carbonyl-like compound with a positive charge. We call this an oxocarbenium species. Okay. Now, we want to talk briefly about the kinetics of this reaction, and there are a few options. Your text takes you through and considers the possibilities in the kinetic evidence. I'm not going to beat around the bush. I'll just show you what the what the option is. For acetals where the OR group is not a good leaving group, you really need specific acid catalysis. That is, you need the specific acid, H3O+, to do the protonating of the potential leaving group prior to the rate determining step, because the leaving group OR- is such a cruddy leaving group. So if we were to sort of lay out the kinetics of this kind of reaction, protonation would be a fast pre-equilibrium followed by sort of slow elimination to get the oxocarbenium species. And then you'd sort of have fast addition of water to that oxocarbenium species. And then also fast deprotonation of that positively charged intermediate to give you the hemiacetal. And of course, we could go on from the hemiacetal all the way down to the free carbonyl compound. But in general, specific acid catalysis is what is observed here. Let's see. Hammett analysis of benzaldehyde diethyl acetal. That is, you take the benzene ring and you put an X group on there. gives you a row of minus 3.3, which supports the buildup of substantial positive charge in the transition state of the rate determining step. And we said that this step, the elimination step, is slow, which would involve buildup of positive charge on the, we say on the carbonyl oxygen, but remember that you've also got this resonance structure where more of the positive charge is on the carbonyl carbon. So the kinetic evidence is consistent with the elimination being the slow step. However, if your OR group is a good leaving group, you can start to see general acid type catalysis. So let me give you an example of a case where your OR group is a decent leaving group. So what if it was paranitrophenol or something like that? Let's actually just make it phenol so that it's not too challenging. What happens here for OR groups that are decent, we tend to see general acid catalysis. And what this means is the acid is involved in the rate determining step. So that would be a beta elimination step. As the leaving group leaves, it gets protonated by the acid, and that's the slow step. Okay. So this sort of addresses the issue of how do you know when you need to protonate first versus when you can protonate as the leaving group is leaving. It's all about how good the leaving group is, and you should be pretty good by now at recognizing good leaving groups. Questions you want to ask about that? Okay. Beta elimination steps are seen all over the place, including in the Jones oxidation. I'm not going to show you the whole mechanism or reagents or whatever for the Jones oxidation, but the key intermediate is this chromate ester, where you can think of all of this as being a good leaving group, and then you have a base removing a proton that is beta to the good leaving group, and the leaving group leaves, and you have now a new pi bond, H3O plus, and CrOH minus. Okay? A similar sort of issues happens in the Swern oxidation. If you don't know about the Swern oxidation, you'll learn about it, I think, in 553. But the key intermediate in the Swern oxidation involves a sulfonium ylide with a negative charge on a group, the methyl group adjacent to the sulfur. And again, you can think of this part as being the leaving group. This is alpha, this is beta, and you get sort of an intramolecular reaction where you make a new carbonyl compound, and your leaving group is actually neutral dimethyl sulfide. And kinetic isotope effect studies support the removal of this proton as being sort of the rate determining step of that reaction. Okay, what else? Anything you want to ask about that? in the Swern oxidation, the leaving group is dimethyl sulfide. It acts as a base. It acts as base and leaving group. Kind of weird. Kind of funny. The deprotonated methyl group removes that beta proton, create the new pi bond, and then lone pairs go on the sulfur. All right. There are some other examples of eliminations that involve larger sorts of systems, not now beta eliminations, but longer. This is sort of the elimination analog of the conjugate addition reaction. Yeah. Okay. So here's your leaving group: alpha, beta, gamma, delta, or maybe 1, 2, 3, and 4. But if you have a base, you can remove this proton, and you can do an E2 kind of like elimination, only you were further away. And the reason this works is because you can form a conjugated pi system. In terms of the orbitals, right, you can think of if you remove this proton, then you would have an allyl type system. And if you drew the resonance structure of that allyl system, you could put the pi bond here and the negative charge on the beta carbon, and then it's just a beta elimination. And this highlights a concept called Vinylogy in organic chemistry. Maybe you'll learn about this in 553, but it's the idea that if you take a typical functional group like an alkyl halide and you put a double bond in between the leaving group, so let's split apart the alpha and beta carbons and put a double bond in between them. The molecule here will have similar reactivity as this molecule in terms of it'll be able to do elimination reactions because you've got this vinyl group in between the two. Vinylogy is like analogy. It's an analogous group. It undergoes analogous chemistry, but we call it vinylogous. I don't really ever use that word that much, but some synthetic chemists will. Okay. Any questions you want to ask? So let's talk for a little bit about some elimination options. What we know about E2 and E1 is that the appearance of product for E2 depends on the reactant and the base, whereas for E1, the kinetics are such that we have no dependence on the base, just on how much reactant you've got. We would expect for E2 reactions that there would be a significant primary kinetic isotope effect for the beta proton, the one that gets removed in the transition state, whereas there is no kinetic isotope effect at the beta proton for an E1 reaction, because in an E1 reaction that deprotonation happens after you get to the carbonyl carbon. We should point out that elimination and substitution can compete with each other, and so you have to be aware of that. I think you're aware of that from undergrad organic chemistry. If not, you can look at the text to give you some more information there. However, there is another variant of E1 that actually you need to know about, because it's on a mechanistic continuum with E2 and regular E1. And this is E1 conjugate base. It still has only first order kinetics, but deprotonation happens first in a rapid step and then slow elimination. So a good example of this is when your proton that is beta to the leaving group is also adjacent to an electron withdrawing group. Notice here we're talking about distance away from the leaving group. I'm not talking about the alpha carbon of the carbonyl, but rather alpha is the one connected to chlorine, and then beta is the one adjacent to that. But because the beta proton is adjacent to the carbonyl, it actually is faster to remove that proton. I guess I'll draw the enolate resonance structure, whatever. And then in a second step, you see elimination of the leaving group. And this is the step that is slow. All right. And so if you want to look at the kinetics of this step, you've got a pre-equilibrium to an intermediate and then a slow step. You could use the steady state approximation for this intermediate. And if you do that and go through the math, which you should already know how to do, we don't need to recapitulate here, one of the things that you see is now the base is involved in the, let's say, negative and then BH. Base is involved in the equilibrium, and the conjugate acid of the base is also involved. So the kinetics for the E1CB reaction, what you observe sort of depends on the relative rates of the reactant. So up here, relative rates of these various steps. So up here I showed you, oh, this is a unimolecular reaction that only depends on the concentration of the reactant. And it looks like that was wrong, because here's actually the kinetic expression. So I'm going to have to think about that for a minute. But in any case, it's now 11:50, so I guess we'll be done. Any questions you want to ask so far, except on this thing that I'm confused about? The difference between E1CB and E1 is, with E1CB, the slow step is leaving group leaving. The fast step is deprotonation. With E1, the slow step is, so the slow step is the same in both cases. It's just which happens first, right? In E1, the leaving group leaves first, and then you have rapid deprotonation. In E1CB, you have rapid deprotonation, and then the leaving group leaves. And next time we're going to set up one of these more O'Farrell-Jenks diagrams to reason our way through it, and hopefully it'll become clearer there. All right. Any other questions, things you want to ask? Why is the first step fast compared to the second? I think it really has to do with the pKa of the proton you're removing. In a regular E2 type reaction, a proton that's on an sp3 hybridized carbon would normally have a pKa of about 45 to 50. Probably it's beta to the leaving group, so that pKa is less, but it's very difficult. It would be very difficult here to remove the proton entirely before the leaving group left. In other words, you need sort of that cooperation of the leaving group in order for the proton to be removed. In contrast, the pKa here is somewhere around 20. And so it should be a little bit faster for the base to remove this proton, and the leaving group doesn't have to leave as much before the deprotonation can happen. Yep, you bet. And it turns out in my notes I have a little bit more on how to interpret this, and under certain conditions, we can get to the unimolecular equation that I drew for you above. So I'll explain that more next time. How did they get this methyl group here to be negatively charged? Yeah, so you need a base. In the Swern oxidation, let's see. I want to get my notes. Right, so the Swern oxidation actually starts with, you have DMSO, and then you have oxalyl chloride, and the oxalyl chloride is all about turning this oxygen into a good leaving group so that the oxygen of your alcohol can attack the sulfur. And that's how you get here. So that's how you would get to this particular intermediate. Then you need a base to remove that proton, and that gets you here. Now, how is that possible? It has to do with the fact that that sulfur is electron poor. And so in any molecule that's positively charged, if you can put a negative charge on the adjacent carbon, that can be a stable situation. This is called an ylid. And it's actually not that different from the ylid in the Wittig reaction. Cool. Anything else? All right, well, have a happy Monday. We're almost done. You have almost survived 552. I'll get your test scored later today, and I will see you next time.